what we're going to look at here is two-dimensional motion. And the important thing for us to understand in two-dimensional motion is that the horizontal motion is independent of the vertical motion. So let's look at an object that we shoot horizontally. So as we see, as it flies through, as it goes through the air, it would have a trajectory like that. Okay, and if we look at the horizontal and vertical motion at each point, at these 3 points in space, it'll help us understand how to solve these problems. So the blue dot there represents the vertical motion at the beginning. There's no initial vertical motion, but there is horizontal motion here. In the next slide, we notice that now there is some vertical motion downward, but the horizontal velocity remains constant, as it does through the very last vector as well. So the important thing here to recognize is that the horizontal motion remains constant. We've got constant velocity in the horizontal, but in the vertical, we have acceleration downward. So if we separate out the horizontal from the vertical motion, here's what we notice. We notice that if we take the horizontals and move them over there, and the verticals and move them over there, we can solve these types of problems a little easier. All we're doing here is we're just separating the horizontals from the verticals and using the fact that we talked about earlier, that the horizontal and vertical motion don't affect each other. They're independent of each other. So that's why we can do this. That's why we can separate out the horizontals from the verticals. Notice that the acceleration in the horizontal should be 0 if the velocity is constant. In the vertical, the acceleration is downward because the velocity arrows increase on the way down. So let's look at a problem in 2 dimensions where we're launching an object horizontally. So this is an object shot horizontally from a 20-meter height of 10 meters. I'm sorry, it's an object that's shot horizontally at 20 meters per second from a height of 10 meters. So we're going to find the time of flight and the horizontal range. So step 1, what we'll do is we'll draw a motion map. Our next step is to include the components, both horizontal and vertical. Then we're going to separate the horizontal from the vertical so that we are just looking simply at the horizontal and the vertical values. Motion maps, I should say. Next, we'll separate the horizontal from the vertical, as we've just done, and we'll label what we know. All right, we'll label the fact that we've got the acceleration that's 0 in the horizontal and the acceleration that's downward. Okay, so when we label what we know, we'll actually find that the accelerations are equal to 0 in the horizontal. The velocities we know. We know that in the horizontal, the object's moving 20 meters per second. So it's always moving 20 meters per second. In the horizontal. In the vertical, we know that this acceleration, the value of the acceleration is acceleration due to gravity, and that's always negative 9.8 meters per second squared. We also know that in the vertical, the initial velocity, V initial in the vertical, will be equal to 0. Okay? So, as we use this strategy in the vertical and horizontal, we remember that we have to write out, let's use our strategy first in the vertical, X, V initial, V, A, and T. X, if we're going to consider the final position down here to be our final position, then, and if this is vertically my initial position of 0, then my final position, since it's beneath it, is going to be negative 10 meters. So we're going to put negative 10 meters there. The initial velocity we said earlier is equal to 0. The final velocity we do not know. we remember that our acceleration due to gravity is negative 9.8 meters per second squared. And so we don't know the time. So let's circle the things we know and the thing that we're looking for. So we know from these, our knowns and our unknowns, that the equation that we will have to use is this one. X is equal to x initial plus v initial t plus 1/2 at squared. So this becomes 0, or that's 0, and that's 0. So we simply have x is equal to 1/2 at squared. So if we solve that for t, that becomes the square root of 2x over a. I highly suggest that you memorize this equation because it's the equation for the time of flight for an object shot horizontally and also the time of flight for an object that's just being dropped. So we'll plug in our values. 2 times negative 10 meters divided by negative 9.8 meters per second squared. And for that time, we get 1.43 seconds. So we found actually the time of flight for this object. The other thing that it asks us to find is the horizontal range. Now we can also use a strategy in the horizontal for this. So let's write out again. So this is for the horizontal. Again, really important that we separate out the two different motions. We've got x, v initial, v, a, and t. X we don't know. That's what we're looking for. Our initial velocity is 20 meters per second. So is our final velocity. It's 20 meters per second. And our acceleration is 0 meters per second squared. And we know the time is going to be 1.43 seconds because we get that from the vertical motion. So again, we would use the same equation. X is equal to x initial plus v initial t plus 1/2 at squared. Okay. We know that the initial position is going to be 0. The acceleration we know to be 0. This velocity, the initial and final velocity, are both 0. So really this equation just becomes x is equal to vt. Because both the horizontal and vertical velocities are 20 meters per second. So they're a constant. This is the equation for average velocity or constant velocity. So now we can simply solve this equation. Let's put it over here for more space. X is equal to vt. So to find our horizontal range, we would simply take the velocity that we got, our velocity here, which is 20 meters per second. Again, it never changes, 20 meters per second, times a time of 1.43 seconds. And for that, we get a horizontal range of 28.6 meters. All right, let's look at another example of two-dimensional motion. Let's look at an object that's shot from ground level at an angle. As the object goes through its flight, we can look at the horizontal and vertical components. In red, we've got the horizontal, and blue, we've got the vertical components. And so it's got initially some horizontal velocity and a vertical velocity that's upward. Notice that the horizontal velocity is the same from that point to that point, and it continues to be the same. The horizontal values become constant. And once again, they are independent from the vertical values. So if we separate out the horizontal and the verticals, we get this type of motion. We've got constant velocity in the horizontal, but a velocity that increases on the way up, stops, and then increases on the way down. So our acceleration obviously would be 0 in the horizontal. On the way up, since the velocity arrows are decreasing, the acceleration arrows would point downward. Then on the way down, the acceleration arrows also point downward because the velocity arrows are increasing on the way down. As a matter of fact, the acceleration would still be pointing downward even when the object is at the very top. Now, in looking at an actual example of an object that's shot at 10 meters per second from an angle of 37 degrees, where we got to find the time of flight, the maximum height, and the horizontal range, we would at first draw a motion map, just like that. We would include the components, separate out the horizontal from the vertical components, label what we know and what we don't know. So, for example, what we can do at the very, very beginning is look at the initial velocities. So if the object's going at 10 meters per second at 37 degrees, we can find the initial y velocity as being 10 meters per second times the sine of 37 degrees, and that would be 6 meters per second. Now, this picture is not to scale, so we'll notice that here when we calculate out the horizontal. So, I'm sorry, that should be the horizontal initial velocity. That would be 10 meters per second times a cosine of 37 degrees, and that would be 8 meters per second. So again, this picture is not to scale. So we find out from this picture, or from this calculation, that the initial horizontal is 8 meters per second and the initial vertical is 6 meters per second. So let's finish labeling what we know. We definitely know that the initial vertical velocity, we said, was 6 meters per second, and the initial horizontal velocity was 8 meters per second. Remember that the horizontal velocities are always constant, so each one of these is 8 meters per second. And because each one of these is 8 meters per second, that means the acceleration is always equal to 0 in the horizontal. Let's go over here to the vertical. If we look at the vertical velocities, once again, we know the initial vertical velocity is 6 meters per second. When it gets to the very top, this velocity will be 0 meters per second. And because things are symmetrical, this will be negative 6 meters per second. Negative because it's going downward. All of these accelerations would be equal to negative 9.8 meters per second squared. So let's separate our calculations from the horizontal and the vertical. Now we can start either with the horizontal or the vertical, depending on which one gives us enough information. I'm just going to happen to start with the vertical. Let's see if it gives us enough information. So let's write out our strategy: x, v initial, v, a, and t. In the vertical, we'll notice that our x, we don't know. We don't know how high it's going. The initial velocity in the vertical, we said, was 6 meters per second. The final velocity, if we're going to figure out just from ground level up to there, the final velocity would be 0 meters per second. Okay, and the reason why we're just doing the first half of the object's trajectory is that we are just going from the bottom to the top and we want to find the maximum height. The acceleration is going to be negative 9.8 meters per second squared, and the time we don't know. So if we want to find, first of all, the maximum height, we would circle that because that's what we're looking for, and circle the things that we know and we don't know. And the equation that would be helpful there would be this one: v squared equals v initial squared plus 2ax. And to solve that for the maximum height of x, we would get v squared minus v initial squared over 2a. I'm running out of room, so I'm going to leave the units out. Normally, in the best of all worlds, we would leave the units in. Okay, and in this case, we get a maximum height of 1.8 meters. That's our maximum height. Now let's find the time of flight. The time of flight we know we can find because not only do we have this maximum height of 1.8 meters, we have the initial velocity, the final velocity, the acceleration, and the time. So let's go ahead. We've got 3 of the 4 unknowns, or 5 unknowns. We can therefore solve for the time using this equation. V is equal to V initial plus AT. Solving that for t, I would then get v minus v initial divided by a. And so t would equal negative 6 meters per second minus 6 meters per second over an acceleration of negative 9.8 meters per second squared. And that would give us a time of 1.2 seconds. That would be the time of flight. Finally, we will solve for the horizontal range. And because the horizontal range is in the horizontal, obviously, we will use our horizontal motion map. So if we use our strategy in this case, we would write out x, v initial, v, a, and t in the horizontal. Again, I gotta focus on that motion map because it's the horizontal motion map. The horizontal range is what I'm solving for. The initial velocity is 8 meters per second. The final velocity is 8 meters per second. The acceleration is 0. And the time I don't know. So if I'm looking for these variables that are known and unknown, I would therefore use this equation. X is equal to x initial plus v initial t plus 1/2 at squared. This part goes away because the acceleration is 0. We assume the initial position is 0. So therefore this equation, because this initial velocity is constant, I can just write that equation as x is equal to vt. And if I solve that, let's solve it down here, x is equal to vt. My horizontal velocity is a constant 8 meters per second. The time I would get from here, so we would plug that in, 1.2 seconds. And we get a horizontal range of 9.6 meters.